Does it work? Does it work the real time? You need to hold it. I mean, the one thing that you need to make sure is that where the speaker and microphone are, whether they're close or not.
No, I can see like when I'm looking at my microphone display, right? I can see that it's picking something up. When I look at the receive signal, there are no spikes. I'm sure. So I'm trying to figure out why.
What do you mean spikes?
No, I mean for seeing the pulse train.
Yeah.
It doesn't show up on the receive signal, but I can see like I'm looking at the microphone, like it's taking in something.
So it's not recording the right one. So you need to make sure that Pi Audio is actually recording your microphone, not some other device.
No, I tried my external microphone and I got close to the speaker. I can see like.
So what I'm saying is that you need to make sure that Pi Audio is picking up your internal microphone and not some other random device. Yeah, line in or something else. Or maybe some, I don't know. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Welcome to EE123 lecture 10. Woo! Okay. Today's my favorite topic. No, seriously, so I thought DFT was my favorite topic, but then I was working on these slides, and I was like, whoa, this is actually my favorite one. Time-dependent Fourier transform. Before this, a few announcements. Midterm, 222 this year. Open everything, so you can accept things that controlled by a processor. So no phones, no computers, things like this. No outside world connection. Whatever you bring in, you can use. It's going to be in this room. There's going to give you a lot of space. It's going to be quite awkward to bring too much stuff. So make a cheat sheet. Really recommended, because you don't want to, in the time that you have, to start looking at books and stuff like that. Okay? So please prepare something. Don't bring everything, but you can if you want to. Okay? It's going to be from 10. Yeah.
Will some like basic Fourier transform pairs be given to us, or should we write those down?
The what?
Like, will it be provided for us, like some Fourier transform pairs?
I'm not going to provide you anything. You're just like, whatever we covered in class, you need to know.
Okay.
So, yeah, you can prepare yourself a cheat sheet. You can bring your book. You can do whatever. If we feel like, it will be faster, maybe we'll add something, but we're not going to make a cheat sheet for you. Okay. It's going to be from 10 to 12. Okay, so it includes the section. If you have issues with this, let me know, but you shouldn't be having any issues with this because it's a section. It's part of the class. Like you knew that you have to be there. So, yes. John had some comments on the homework. Do you want to speak out?
Yeah, just please make sure that all of your homework pages are scanned so we're not missing some pages, and that you make it legible. So if the grader can't read your homework, it's a problem, and then we have to hunt you down. And also, please turn in the self-grade if you turn in the homework so that we can give you credit for it. Good job.
Actually, let me reinforce some of the things. If you don't scan well, then we'll remove credit. Okay, so if it's not intelligible to read, we're not going to chase you. We're just going to zero for that part because it's really a problem to chase if, just people over and over. So just take the effort and scan it appropriately when you submit it. So that's more manageable for us, but requires just so much little effort from you, and really you should be doing this. Like, look at what you've been scanning and submitting because it's your work, and you need to self-grade it. So just try to self-grade from the submitted homework, and if you can't, then that means that there's a problem. Okay, because that's how we're going to take a look at it as well. How's the lab going? Who has not started yet? Be truthful. That's very good. Who do not think that they're going to be finished by Thursday? Unacceptable. I'm serious. We're giving you 2 weeks for this. It's unacceptable not to have it done, especially because we increase the amount of grading that you're going to get for this. So, and there's some questioning you're going to get and so on and so forth. So it's unacceptable not to submit it on time. Please submit it on time. And that means that when we give you the lab, then you should start kind of look at it and see, how it goes, and then start working the first week a little bit on it. There's going to be technical issues. There's always going to be technical issues. You can never count on the fact that you can do it in 2 days at the end, because you have to go through the technical issues. And we give you the technical issues on purpose. Not really, but that's what happens. That's real systems, okay? Real systems have that. And this is part of the learning here, is how to debug stuff that's real. Okay? This is part of this experience that you're going to get, whether you want it or not. But this is life. There's always debugging. There's always connectors problems. There's always bugs. There's always drivers not running. Yeah. Midnight on Thursday. Use then the labs on Tuesdays and Thursdays to debug that stuff. Okay, that's where we're there. We got lab assistants from previous times to do this. I also beg you, if you want to do lab assistance for the next year that can be offered, please think about that too. But the whole idea is to give you as much help and support as possible. So start early, debug through these issues, and then move on. It's the audio that you need to debug really well. That's the problem. Next lab is going to be the software-defined radio that you'll have to debug. And some computers always have issues. I don't know why, but they always do. But we want that for you to work. We'll help you. We'll help you go through these. But you cannot leave it to the last minute. I beg you. We spent an immense amount of time on these labs to create them and also modify them and make sure that they're current. So, it's a really good experience. And every feedback I get from this class is that the labs were the most substantial things to do. So do them, because that's what it's all about. Okay. Any more questions? No? Last time we didn't finish a few things. We talked about frequency analysis with the DFT. Realized that the length of the window you're going to pick is going to give you the spectral resolution. The type of it will give you kind of the trade-off between the side lobe and the main lobe, right? Each one of them is slightly different and depends on the application. If you want to differentiate with things that are close to each other, you need something which has a low second side lobe and a narrow lobe as much as possible. If you want to distinguish between high dynamic range and far away, you want maybe your side lobe to decay really rapidly. And that's not even in the presence of noise. Remember, when noise comes in, that's going to get worse. The one thing that we also covered is the zero padding approximates the DTFT better. It doesn't give you extra information. It's just a form of interpolating the spectrum that it looks nice. It looks closer and closer to the DTFT of that sequence that you have. Okay? So I gave you this beautiful MRI example where, yes, zero padding did not give you information. It just was a blurred image once it was enhanced. Okay? So there's this slide here about how to debug things in solutions. So I don't want to spend too much time on this, but if you have spectral error from aliasing, for example, then what do? You have to filter the signal in order to use an analog low-pass filter in order to mitigate with this, or increase the sampling frequency. If you have insufficient frequency resolution, you want to increase your window, or use a window having a narrow main lobe. Spectral error from leakage, you either use a window having lower side lobes, depending again on what is the application, and of course you want to increase the size of the window again. But remember, that's what we're going to get today. When you increase the size of the window, if you have something that's non-stationary, signal that changes over time, does that happen? Yeah, my voice changes over time. Right? Here's an example. Then increasing the window, not necessarily going to improve your resolution. Okay. If you have missing features due to spectral sampling, again, either increase L. So everything is about increasing L because that really reduces things. But Also, if you want to be able to see those fine structures and the sampling is not exactly on those, small peaks, then you might also want to do some zero padding to have a better depiction of the spectrum. Okay. That was summary last time. The other thing I want to talk about is some subtleties with filtering and processing with the DFT. And it's something that maybe you don't think of, but I'm going to stress it out over and over again. When you work with discrete samples, you have to be careful. You have to be careful about edges, and now sequences are finite, so all these transitions can cause issues. There's all sorts of subtleties that you've got to be aware of, and this is really important when working with the systems, especially because you're going to implement them. So let's say you have a sequence of X of n coming into some system response, and then you got some Y of n out. Let's say that system here is implemented by an overlap and save type of a filter. Now, overlap and save only then correspond to an FIR filter, right? Okay, so it corresponds to an FIR filter. And the way it's implemented is filtering using the DFT. So assuming that there's no aliasing, you only save you save you do the right filtering, and you save only the valid linear convolution effect of this filter. And this is how you're going to implement it. You're going to take a chunk of data, a window. I think this is size 256, and you're going to compute its DFT, and then you be multiplying by that window. So is this what kind of filter is this? What? But it has stuff here. Still low pass, right? Because with the DFT, everything is shifted, right? So remember this. This is the high. The middle is the high frequencies, right? Yes, it's still a low pass. Okay, everything is shifted in the DFT. Remember that. That's again another weirdness that you have to kind of think of when you do things. And sometimes you don't want to do FFT shifts just because you don't want to think about it. Okay, so it just wastes time to move data around. Okay, so you're going to multiply by this. That looks to me like an ideal filter, right? You pass certain frequencies, you don't pass certain frequencies. Is this an ideal low-pass filter? Right? It looks ideal to me. Can it be ideal? Well, why is this quiet? These are all things that are discrete, that can mess with your head. So think about it. I compute DFT, I know these frequencies, I pass these frequencies. Is this an ideal low-pass filter? We don't know what's happening between the samples of the DFT. Because DFT samples the DTFT, but samples at points, certain points. But we don't know what's going on in between. It can go, loco between, right? It can go crazy between these two samples. It can jump to infinity, maybe. I don't know. Maybe. Turns out it cannot really jump to infinity. But the thing is that there's going to be issues with this, right? So it cannot be. This is an FIR filter. FIR filter cannot be ideal low-pass filters. Cannot. They're finite in time. It's just not possible. Okay? So remember that. Okay? But the one thing you can do is look at the impulse response of this filter, right? Is it going to do what I actually want? Is it going to have a nice frequency response like I'm expecting it to have? What's the frequency response of this? Sorry, what's the... Yeah, that's right. Yeah, that was a trick question. What's the impulse response of this? A periodic sync. Yeah, it's a sample periodic sync, right? It's a sample periodic sync. That's great. You guys rock. And so we went. If I'm going to filter with this sample periodic sync, right, I should get like a nice frequency response, right? Right? It's a tricky question. It's tricky. Because here's the thing. This is real. Right? This is not magnitude, actually. This is real values. What about the phase? I didn't put any phase here. What happens if I don't put any phase? Here's the impulse response. If I don't put phase, so now it's going to be circularly, like it's periodic sync, right? So I'm going to have effectively an impulse response that, yeah, it's a periodic sync, only it's not centered in the middle. It's kind of like a zero delay filter, kind of. But because it's a zero delay filter, because it has no phase, it's supposed to be zero delay. Right? So it's non-causal, but of course it's going to be causal because I'm going to just filter. It's an FIR. It's going to be causal. And things will wrap to the other side of the filter. And so, yes, this is my filter. It is a periodic sync. But now, yeah, I'm gonna basically convolve with that thing. I'm performing a linear convolution with this thing. Is that something you want to convolve with if you're going to do a low-pass filter? I don't know. It uses sample 0, but then like sample 250 away at a high amplitude. Doesn't look so low-passy to me. You see what I'm saying? If I added a linear phase, then thing would have centered in the middle. Then it would do the right thing with a delay of 128 samples. It will have a delay, but it would kind of do the right thing in a convolution point of view. But now I'm convolving with this thing. And so if you want to actually know what is the DTFT, well, you take this sequence and compute the DTFT. You want to see it? You want to see it? Yeah? No. I'm going to show you. You're going to do it at homework. No, actually, I'll show you. This is the DTFT. Well, as it turns out, the sampling is exactly the right places. When you sample, this looks at the sampling, like if you compute the DFT of this, it will give you, flat and, zeros. But the DTFT also evaluates stuff in between. And look, the stuff in between is all this crap. This is a terrible low-pass filter. It's a terrible low-pass filter. And if you only added a linear phase, things would have been much more regular. Okay? So, discrete, you have to think. Does this make sense? Yep. Yep.
So, that DST right there.
Yep.
Zero for the phase everywhere.
Yeah, 0 for it's like it's just you ones and zeros they put. Yeah, it kind of makes sense, right? I want to pass some frequencies with one, want to pass some frequencies and want to attenuate some frequencies. So yeah, a trivial thing would be, I want to deal, like put ones and then put zeros. But you have to know what's actually is happening in the time domain. The time domain, you got circular shifts, right? It's not a linear shift. It's a circular shift. And that's the case of the discrete. If I did that to the DTFT, like if I could have computed the entire DTFT, yeah, that would have worked out because I would get a non-causal filter that would be centered around 0, and that would be okay. But because now things are discrete, finite, I get a circular shift, which completely screws up my filtering. Okay, so that's the thing that you have to be aware when you do digital, as opposed to 120 when maybe you didn't think about that. Yeah.
Would it be okay if we use inputs that have the same length as 256 with a switch set? Is that DFT?
No, this will be the convolution. I mean, like if you implement a linear convolution. So we're implementing a linear convolution using a circular convolution. Remember that, right? So a linear convolution will do this. If I wanted to do circular convolution, maybe it would have worked out on a short sequence. Yeah.
So you said in order to get like the best behavior out of this, you have to shift by 128. What happens if that's not acceptable? It's not acceptable to have a delay like that?
Well, you have to come up with a different filter then. So that maybe has less delay, but every filter will have some delay, right? And we're going to get that when we talk about systems and filter design. Yeah.
So if we're designing filters by like making coefficients like that into the frequency, and then we look at the impulse response, do we like check the frequency response?
Absolutely.
We kind of observe that in the impulse response.
Well, right. You could absolutely do this, and we're going to learn techniques to design FIR filters that are optimal, also in some sense. We're going to check that. But that, like, if that sounds perfectly reasonable thing to do, but if you think about it carefully, it is not a reasonable thing to do. And so all these things can happen in the future in other type of system. And so just want to tell you, you have to really think in discrete time what you're doing. If you're using DFT, don't take that as granted. People say, yeah, DFT is like, it's convolution, convolution become multiplication. Not true. It's circular convolutions. It's going to have an effect. Any phase in the one dimension correspond to a circular shift in the other dimension. That's going to have an effect too. So remember that, because it's going to come up. Okay. All right. Okay, last time, frequency analysis, DFT, windowing, zero padding. Today, time-dependent Fourier transform and Eisenberg boxes. We're going to talk about boxes. Okay, today. Now, here's the thing. The DFT, if you think of the DFT is really one out of a large class of tools, of transformations that people have developed to do all sorts of things. One thing you can do is for analysis, right? I showed you. We can do DFT to do frequency analysis. You can also use it to compression, and like John showed how to compress things using the DCT or the DFT in the section on Monday. Okay, so the DCT, discrete cosine transform, is used heavily for JPEG compression. Your cameras are, constantly taking DCT transformations whenever you take a picture, and then when you do Skype and things like this, you're going to see the wavelet transform being used over and over again for doing these compressions. It's also going to be used for denoising, so removing noise out of signals. Transformations are extremely powerful tools. Detection, if you want to see a certain frequency, what you do is you compute a DFT, right? Because then things will show up. Or you can use another transformation that fits the particular type of signal that's coming in, right? If I have signals that are like, square waves, maybe DFT will not be the perfect one. Maybe there's a transformation that has, a good way to represent square waves. Recognition, so being able to interpret things, so creating features that you can then train on, use it for classification and things like this. Okay, so edge detectors, all these apply certain transformations. And then if you want to approximate a signal, and that actually relates to the compression, if you want to approximate a signal using a sparse number of coefficients, that if you have this dictionary, then you can just store the coefficients. I mean, that's another way that people use transformation. And I have to say that sparse representation has been really the hottest topic in the last 15 years in signal processing. So this is a really important tool. But here's an example of spectral analysis that you've seen before. This is a spectrum of a bird chirping. You heard it? You want to hear it again? It's kind of nice. Okay, you heard it? You want to hear it again? Okay, one last time though, because we need to move on. Okay. So if you just look at the spectrum of this bird chirping, right? So you look at this, yeah, that's great, nice spectrum, right? So yeah, the most of the frequencies are, around that, that's part of the spectrum, and that's great. But if you hear it, it's way more complex. Right? There's more to it, right, than just looking at the spectrum. Okay? So when we just look at the spectrum, we have zero temporal information of what is going on. Like, I stare at this. I don't know when things are going on. I know, yeah, those frequencies are participating, but I do not know where. But obviously, things were changing. It was like a bird chirping. Frequencies were changing over time. And I cannot see this right now. Okay? Any ideas? Yeah, but can you see it? Like, do you know? I mean, of course it's encoded in the phase. Right. It is encoded absolutely in the phase, right? Because where are things? But the phase is all added from all these combinations. I mean, it's like hidden in the phase. The information is there. I mean, the information is also in the time domain. In the time domain, I can see like amplitudes, but I don't know frequencies. Right? I see amplitudes, but I don't know frequencies. There, I see frequencies, I don't know positions. Right? So any ideas of how to maybe fix that? Nice. Right. Nice. Time-dependent Fourier transform, he said. But I mean, yeah, but like whatever, we're going to develop this. But what does it mean, even? Time-dependent Fourier transform. Absolutely. Break it into sections, compute Fourier transforms over those sections, right? Now you start thinking, well, wait a second, but last lecture, Mickey said that, that my spectral resolution is going to depend on the window size I'm going to pick, type of windows, right? All sorts of stuff like this. The ability to distinguish between frequencies are going to depend on how I'm going to take, but that signal is not stationary. It's changing over time. So all these things now come to play. Okay? So yes, you can, but you're going to have limitation on the ability to resolve things, okay? And those are inherent. Okay, so that was a great idea, and that was a fantastic idea. Okay? To get temporal information, we use part of the signal at every time point. So what we're going to do now is the following thing. We're going to take our signal and multiply it with a window. Okay? And then compute the Fourier transform. Continuous, like the discrete time, the DTFT. Okay? So it maps this chunk that I'm going to get into omegas, right? If I take a certain sequence, like crop it, it's going to map to omegas. But I'm going to shift that window, so I'm going to have now two variables that's going to come out. One is omega. Omega is what is the frequency. The other one is an index where this window is shifted in time. Yes? What? Close bracket. This one? No. This is actually a good one. So this is a discrete. This is a continuous variable. This was intentional. Okay. This is the continuous variable. This is a window. This is not omega. This is W. I think. Yeah, it's W. Okay, this is omega and this is W. You see this thing here? That's the difference, I guess. Wow. Okay, so the idea here, and this is described here, it's a mapping. It's a different mapping now. I map a one-dimensional signal into a two-dimensional space. I lift it to a larger dimensional space. If you think about this, it's called lifting. In some other, like you'll hear in mathematics, people do lifting operations. This is a lifting. You take one-dimensional space and you embed it in a two-dimensional space. Okay, and this two-dimensional space maps x of n maps x of n into capital X of n and omega. Okay, so that's a two-dimensional space. Okay, so this is interesting. And to do this, what you only do is you're going to have your sequence and you're going to multiply it by a window, compute the DTFT, and then slide your sequence. Compute the DTFT, slide your sequence by one sample, compute the DTFT, and so on and so forth. Okay. Now, this is called the time-dependent Fourier transform or the short-time Fourier transform. There's various words or things that people call it. And that's very interesting. So if I look at this and I map this as an image now, because how do I display things in two dimensions? I'm going to map it into an image that the magnitude of the result is displayed as intensity. Black meaning low intensity, white meaning high intensity. And I'm going to look at this. And this is how it looks like, the chirp. Okay? Now, things are much more interesting. Right? Things are much more interesting. Now I can see the chirp changing, like the frequencies change over time. Right? This is gives us more understanding of what the signal actually is. If I now look at cross sections through this spectrogram, waterfall, ShortTime Fourier transform, time-dependent Fourier transform, all these words representing exactly the same thing. If I look at a cross section, I'm plotting a different spectrum, effectively, for different parts. Okay? Does this make sense?
Is it still complex value?
Yes, absolutely.
So what?
I'm just showing the magnitude response, but there's also a phase response, too. And people do a lot of cool stuff when they do like all this voice manipulations. For example, if at every chunk you're going to remove the phase, you're going to have like a robot kind of sound. Right? And you can like do various things, to compress the, the time while preserving pitch and things like this using those ideas. Okay, so when you're on your phone, when you do like 1.5 or 2 times, like listening to a book or a podcast or whatever, you can implement some of these. I don't know actually how to implement those algorithms, but one of the ways is using those ideas. It's possible to preserve pitch and things like that. Okay. This is very interesting, right? Representation. And it maps a one-dimensional space, one-dimensional signal into a two-dimensional space. Okay, remember that. Which is interesting because there's probably things here that if I put in cannot be represented back in a one-dimensional space appropriately. See what I'm saying? When you take one dimension and you embed it in 2 dimension, it still lives in a one dimension. Like it lives in a 2-dimensional space, but it has really the degrees of freedom of a one-dimensional space, right? So I can what if I put some stuff here and I want to go back to the signal? Maybe there's no signal that can actually have that spectrogram, right? So you have to think of how do I go back? What is inverting this means even? Right? If you want to do, like with a DFT, yeah, one-to-one mapping, no problem. Here, not necessarily one-to-one mapping, right? Okay, so you have to think about this. Yeah, if you start with 1D computer spectrogram, but what if you apply operation on a spectrogram? I mean, there's not necessarily one-to-one mapping. You have to project, right? Solve a least square problem, something like that, in order to go back. Things to think about. Now, of course, we can write that discretely, too. Okay. So now I replace the omega with something. What did I replace it with? With the usual DFT thing. So now instead of computing a discrete time Fourier transform, I can compute a DFT. And now I have 2 parameters here. Now I have x of sub r and k. K is the frequency components, and the sub r are really where I am in time or in the sequence. What's the index? And the r, if capital R would be 1, then I'm sliding my window at 1 interval. But I can also slide my window with jumps. Okay, non-overlapping windows. That's an option. Or I can overlap by half. Right? You'll see in Lab 2, you're going to implement this type of thing, and you see the advantage of overlapping and non-overlapping. Yeah. No. You could put a jump here too. Yeah, I wanted to illustrate actually this continuous time transformation effectively. I mean, you can also write this there is a representation for this in also continuous time where you have an integral. Right, you compute the Fourier transform over a window signal, right, even in continuous time. But now it's all discrete. Now, this is partly discrete. Okay, I got to go this. Well, I worked a lot on this, so you should watch it at least twice. Okay. So now L is the size of the window that I'm going to be using. Okay. R is the jump, how many samples I'm going to jump. And then there's another parameter is N, which is the size of the DFT that I'm going to apply. So I can also do zero padding, right? So I can like crop a window and then zero pad, then compute the DFT, which effectively gets me closer to the DTFT, and which is the previous slide. All right? It's cool stuff. Let's talk about Eisenberg boxes. So there's really this time frequency uncertainty principle. In continuous time, what it basically says is that there's always going to be an ambiguity between your ability to resolve frequency and to resolve time. And that ambiguity, or this uncertainty principle, is described as sigma t times sigma omega, which is the variance of a Gaussian. So it is equal. It's always greater or equal than half. For Gaussian signals, it's equal to half. And so if I have a Gaussian distribution in time, and I compute its Fourier transform, and it has a certain standard deviation, which is the sigma, it's going to be inversely spread out in frequency, okay, to the sigma. So the sigma in the frequency is going to be 1 over that, okay, with this constant half. Okay, so if I have a certain window that I picked in time, that's going to give me a resolution in frequency. And so effectively, you can think of it as a box with a certain area, which is area is half. And I can never get better resolution than that in both time and frequency. I can zoom in time by squeezing this, but that box will just stretch. But it's like this blanket that you cannot change its area. Like you can just, you can rotate it, you can, if you squeeze it that way, it's going to shrink that way. I mean, it's always preserving area. Like there's just no way to get around it. Okay. In discrete time, it's a little bit more difficult to kind of like, it's a little bit less defined, but in a way, if you think about this, what is the resolution, like what is this uncertainty principle? Well, if I look at the DFT, right? If I look at the DFT, then what I've done really is I've taken n number of samples and I compute from them n DFT coefficients, right? Those represent frequencies. So I took a chunk of size n in time. Now I don't know where stuff is within, I computed DFT on. I don't know where the frequencies are within that window. Right, so I have uncertainty there. But I have good certainty up to 1 over n in the other dimension. Does this make sense? So now if you think of how do I break the time-frequency space of a DFT, how do I break it into boxes? Well, I break it the following way. I have n samples representing, time of length t. And then all of these are translated into DFT coefficients. Each one of them is a chunk of frequency that is spanned over that time. So the area of each box is delta omega times delta t equals 2n. Okay? So if delta t is n, how many samples I have? My delta omega is going to be 2 pi. That's the frequency domain divided by n measurements. So the time uncertainty principle for the discrete case is delta omega times delta t equals 2 pi. And that's not going to change. I can take a smaller time, but now I'm going to spread out my boxes to be bigger, right? And so on and so forth. Does this make sense? Yeah? So what is the effect of zero padding? So one DFT coefficient. Okay, so one DFT coefficient. If like exam questions, I give you a DFT coefficient. Show it where it is in the Eisenberg, in the time frequency tiling. It's called time frequency tiling. Where is the Eisenberg box for that DFT coefficient? And you say, here. Right? That's the box. What happens when I do zero padding? Oh, tricky. Boxes, same size? What do you mean same size? Yeah. So so they change size? But then it means that you have better resolution if they're smaller. But do you really? But if we said that the area should always be the same. But how can you put more lines in the same area? Well, if you make the box bigger, then something has to shrink. Well, but that's having more resolution. So that's doubling actually the measurements. We're zero padding. There's no more resolution. You're onto something, but you're missing one thing. You said, yeah, they should stay the same, but should be compressed. But that's kind of contradictory. So let's say you have these tiles, and it's like 1, 2, 3, 4, 5, 6, 7 tiles, right? And then it says, well, now I zero padded. I should still have the same number of tiles, but I need to put them over here, right? So yeah, I'm going to put 14 tiles here. How am I going to put them? Well, physically, okay, I put 1, 2, 3, 4, 5, 6, 7, and I got 7 more. Well, side doesn't make sense. But what does it mean to zero pad? You get better sampling, right? So the zero padded frequencies are really representing something in the middle of these two. So you overlap them. Okay? So zero padding is in fact overlapping them. It's not shifted to the right. It just overlaps. Okay? So that coefficient represent, the zero padded coefficient really represent that frequency uncertainty, but it's centered around the middle. Okay? It's centered around the middle. But it's the same size. It's just shifted. So I get more coefficients for the same size, right? So the minimum really to represent is n. If I add more zero pad, then yeah, I have just more stuff, but it's really kind of interpolated. Okay? Does this make sense? No? I mean, you're just getting better sampling of the DTFT, but not better resolution. It's just going to be shifted, right? Like you're just sampling in the middle. But each one of those measurements really represent kind of something that's spread out. No, so the ability to resolve frequencies, once you take a certain n, is, there's a certain width, right, to your main lobe. Like if I put you a cosine, right, then you're going to get some width to it. And so you get uncertainty there in where it is really. Because if you have two of them, they might mix and like you won't be able to see where they are. Right? If I have two that are close, you won't be able to resolve them. They're going to look just like one peak. No, it is zero padding. Zero padding is discrete because I'm adding zeros, right? So, but the adding zeros does not give me. Actually, no. What really happens is when I zero pad, this more looks like the continuous time, where I'm just going to slide this box around for each coefficient. But that box is not, it's. So normally in discrete time, that box would be kind of tiled, right? But in continuous time, there's no really much tiling in the sense that you can always have coefficients on the continuum. And that box can move around. So if I want to represent all the possible, everything's going to overlap, but it's going to have that width. Okay? So if I move this by like a fraction, this is going to move. What is zero padding? Is just evaluating them at a few points. That's what it is. So that's why it's overlapping. There's really no something. So which part of the frequency, when I zero pad, am I going to be representing? Like the new samples that, because when I don't zero pad, I have n measurements of frequency. There are samples of the DTFT at n points, right? But they're not like delta functions. We know that in the continuum, they represent kind of a width of uncertainty centered around that particular point in the DTFT. When I zero pad, I'm just evaluating in between. So now that width is just going to be shifted by 1. I'm centered now between the two samples that I had before. Just centered, but my width does not change. My uncertainty doesn't change because I just added 0. Okay? So that's why zero padding doesn't give you any more information. It is just an interpolation. I still have the same time frequency uncertainty. Okay? So I don't have better resolution. It's still, in frequency, I still have the same size boxes. Only they're shifted, moving in frequency. If I zero pad up to the continuum, then it can move anywhere in frequency, but it's the same size box. Now, in discrete time, I can say, I tile everything. Now, this DFT coefficient is representing that width of frequency. I have uncertainty there. Okay? I don't know. That is the variance of whatever that DFT coefficient is representing. And as I zero pad, I just have the ability to kind of center it around a different point. So it's centered around a different frequency, but it has a width. Well, if I zero pad once, factor 2, then I get twice as many coefficients of the frequency. 4, then I have 4 times. And if I have 8, I have 8 times. And if I infinity, I'll just have the continuum. But each box is going to be that width. The width is not going to change. The width is not going to change because my window is constant. Right? I just add zeros to it. Does this more make sense? If not, you can come afterwards or talk to office hours because I want to move on. Does this make sense? No, it's not Z. I wanted to put them on top of it, then you wouldn't be able to see. So I just moved it a little bit. But it's really, this one is kind of like here. Okay? It was just for visualization. Now, if I do a short-time Fourier transform, I break my sequence into pieces. Each one of them, I compute a DFT. Right? The area stays the same. Right? The area stays the same. But now, I compute a DFT over not 8 samples, but 4 samples. So each DFT coefficient now is more localized in time. Each short-time Fourier transform is more localized in time. But now it has worse resolution in frequency. Right? So I've broken it to smaller pieces, have worse resolution in frequency, better resolution in time. Okay, so one short-time Fourier coefficient will have a box that looks like that. And if I would have broken it into 8, then I would divide that into 8. And then this would be even wider. And if I look at just time coefficients would be basically vertical lines. Because I have no information about frequency, but I know the value of the sample. Okay? So it goes from that to that, but it's going to increase. Now, I have an option of R, and the question, what is the effect on R on the tiling? R is how much overlap you've got between windows. What is going to be the effect on the tiling? Exactly, overlaps. Does it change? The fact that I skip, like I overlap windows, does it improve my time resolution? I still use the same size window. It doesn't. But it's going to be centered around a different time point. Right? So effectively, I get a similar thing where now I've got, if I do R that overlaps windows by exactly half, then each coefficient, the new coefficients, because of this overlap, then they will be centered around a different point. But they're going to be the exact same boxes. I'm going to get more coefficients. The thing is, I'm going to squeeze more coefficients into representing the exact same time frequency part. So they have to overlap because of the uncertainty. Yeah.
So it ends up looking, just making sure I'm thinking correctly, it ends up looking a lot like interpolation between...
It is just interpolation because all the information is here. All the information is here because you can go back to the signal domain and redistribute things, right? Like you can compute the continuous time stuff out of this. So it's all about interpolating, but like it's just make it beautiful but not informative. You know? Does this make sense? Okay, we'll talk about more on Friday, where I'm going to continue talking about time frequency titling, and then we're going to move also to the wavelet transform, which right now the boxes here are pretty much the same size in time frequency, but maybe that's not the best way of representing signals. Maybe we want to have in the low frequencies, you know, more time resolution, but worse spectral resolution. And maybe in the higher one, we want the other thing. I don't know. So we're going to move to that and see how we can break that into different shapes of tiles. Okay? See you on Friday. Yeah, if you don't have SD.